Hello, welcome back. In the previous segment, we talked about the first version of randomized primality testing using Fermat-Euler theorem. Okay, our argument was that if we are able to find a witness such that a power n minus 1 mod n is not equal to 1, then we concluded that number n cannot be a prime. Okay, this is just coming straight from the theorems that we have discussed in the past. All right, I wanted to highlight a few things. First of all, if the algorithm says the number n is a prime, remember that's not necessarily always the case. It's not 100% guarantee that the number n will be prime. Okay, it's likely prime. All right. Now the question is, how often will this algorithm wrongly claim a composite number as a prime? Okay. In order to answer that question, I need to provide a few mathematical theorems and propositions along the way. Okay. First, let's start with the very basic one that I need to explain. Here, we are selecting a random number a from 1 through n, excluding n. Okay. This is not the same as z star n, right? Remember, z star n contains elements that are relatively prime to n. Okay, but this one contains numbers that even share some factors with the n. Okay. Now let's think about those numbers that are not part of z star n. I claim that those numbers always satisfy this property. So let me explain what I mean by this more graphically. Okay. Suppose I draw a circle, some kind of a circle, close to a circle. This is Zn. Okay, it is made of numbers from 0 through n minus 1. Okay, and I'm going to put a subset here. Okay, that subset is called Zn star because it's made of numbers from 1 through n minus 1, but are relatively prime to n. Okay, those are the numbers of z star n. All right. Suppose you take an element a here. Let's assume a is an element here. Okay, it means it belongs to Zn but not belongs to z star n, right? That's why I put it outside. Okay, I claim this a will satisfy this property. Okay, let me show it to you why. Okay, first of all, remember a is not part of z star n. That means a must have some factors with n. Okay, that means GCD of a comma n is not equal to 1. Okay, otherwise it would have been part of z star n. Okay, all right. Okay, now we can apply the basic properties of GCD and say if this is true, the GCD of a power n minus 1 n must also be, well, this is, I must say, not equal to okay, if an element is outside z star n, then this element a will satisfy this property. Okay, and if I now raise a to the power n minus 1, the GCD, basic math of GCD tells us that it is still not equal to 1. Okay, now what can we say? Now we have to use an extended equilibrium algorithm session that we talked about earlier. What about the fact that let's assume a power n minus 1 mod n is equal to 1 for a moment. Okay, if it is equal to 1, okay, what I'm trying to say is that if a power n minus 1 is equal to 1 mod n, okay, the opposite of this, right? Which means a power n minus 1 can be written as a power n minus 1 is just some constant times n plus 1, where k is some integer. Okay, that's basically the opposite of this assertion, right? All right, now we can stare at this a little bit and think about the extended equilibrium algorithm for a moment. I mentioned that if you're given two numbers a and b, let me write it here, you can always find x and y such that a times x times a plus y times b is equal to GCD of AB. Okay, and GCD is the smallest integer that can be written as this linear combination of ax and y. Okay, GCD of a comma b. Okay, it's the smallest integer you could write as a linear combination of x and y. Okay, which means we know 1 is the smallest positive integer. That means GCD of a power n minus 1 n must be 1, which is a contradiction because we just proved earlier that GCD of a power n minus 1 n is not equal to 1. Okay. Therefore, this property will never fail if you pick an element a outside z star n. Okay.